Hello, everyone, and a very warm welcome to Pharma Ed. In this explainer, we are going to dive deep into the core principles of pharmacology. These fundamentals are absolutely crucial for your exams like GPAT, so let's get focused and really master them together. So here's our roadmap for today. We're going to kick things off with the absolute basics in Pharmacology 101. Then we'll get into the really cool stuff, how drugs actually work their magic. After that, we'll talk about the critical balance between dose, effect, and safety. Then we'll follow a drug's entire journey inside the body, and we'll wrap it all up with a GPAT quickfire round to test what you've learned. So let's get started. All right, first things first. What in the world is pharmacology? Well, you can think of it as a story with two main characters, the drug and, you guessed it, the body. At its heart, it's the science that looks at this dance between a medicine and a living being, like us. It covers everything, what the drugs are made of, how they work, what we use them for, and of course, those all-important side effects. And this big interaction gets broken down into two key areas. Now this slide, you guys, this is super important. Remember it like this. Pharmacodynamics, with a D, is what the drug does to the body. Its action, its power, its effects. On the other hand, pharmacokinetics is what the body does to the drug, how our system handles it, right? How it absorbs it, moves it around, breaks it down, and finally kicks it out. One is the drug's action plan, the other is the body's reaction. Okay, so a drug is inside the body, now what? It can't just wander around hoping for the best, can it? No way. It has a mission, and to complete that mission, it needs to find a very specific molecular target to connect with. And these are the four primary targets, the main destinations for most drugs. Think of drugs as highly specific keys, and these targets, receptors, enzymes, ion channels, and transporters, are like the molecular locks. The drug key fits into one of these locks, turns it, and either starts a process or shuts one down. That's how we get a therapeutic effect. Now, this table is a goldmine for your exams, really. It breaks down the main receptor families, look at the different ways they work. G-protein-coupled receptors, they kick off a chain reaction inside the cell. Ionotropic ones, they're like super fast gateways, opening and closing for ions. Then you have enzyme-linked receptors, which set off their own cascade, and intracellular receptors, which go right to the control center, the nucleus, to actually change how our genes are expressed. Knowing this is vital. Okay, we know how drugs find their target, but how much of a drug do we actually need for it to work? And more importantly, how do we make sure it's safe? It all comes down to a numbers game. This fundamental concept, the dose-response relationship, tells a very important story. It shows that as you increase the dose, the effect gets stronger. But look, only up to a point. You see that flat line at the top, the plateau? That represents the drug's maximum possible effect. We call that its efficacy. Understanding this curve is so important, and it leads us straight to our next point, a crucial measure of safety. And that crucial measure is the Therapeutic Index, or TI. It's basically the ratio of the dose that can be toxic versus the dose that's effective. To put it simply, a high TI is great news. It means there's a big, wide safety margin between a helpful dose and a harmful one. But a drug with a narrow TI, like warfarin or lithium, well, that's tricky. It needs very careful monitoring because the dose that helps is dangerously close to the dose that hurts. By the way, if you're finding this helpful, please like this video, share it with your pharmacy friends, and don't forget to subscribe to Pharma Ed for more such simplified pharmacology content. Hit the bell icon for notifications. All right, let's switch gears and follow the entire journey a drug takes once it's inside our body. This is called the ADME process, and it's a story that every single pharmacy student has to know by heart. The best way to remember this journey is the acronym ADME. A is for absorption, how the drug gets its entry pass into the bloodstream. D is for distribution, how it travels around the body to get where it needs to go. M is for metabolism. This usually happens in the liver, where the body chemically changes the drug to get it ready for removal. And finally, E is for excretion, the exit plan, usually through the kidneys, when the body eliminates the drug. But what happens when things don't go exactly as planned? We can get adverse drug reactions, or ADRs. It's really important to know the difference between the two main types. Type A, think augmented. These are predictable. They're basically an exaggeration of the drug's normal effect. But type B, think bizarre. These are totally unpredictable. They have nothing to do with the dose, and they're specific to that individual person.
All right, team, you have absorbed so much information. Now for the part I know you've been waiting for, let's tackle some practice questions, just like the ones you'll see in your GPAT exam, to see how well you've grasped these concepts. Are you ready? Okay, take a good look at the options here. Think back to that classification table we discussed just a few minutes ago. Which one of these is the odd one out? Which one doesn't belong to the GPCR family? Yes, if you chose B, nicotinic receptors, you are absolutely spot on. Fantastic job. Nicotinic receptors are classic examples of ionotropic receptors, which means they work by directly opening a channel to let ions flow through. The others, adrenalic, dopamine, and histamine receptors, are all textbook examples of G-protein coupled receptors. Okay, next question. We just talked about this one. The therapeutic index, or TI, of a drug is a measure of its what? What is the single most important thing it tells us? That is absolutely correct. The answer is B, safety. It's not about potency or efficacy or bioavailability. The TI is purely and simply a ratio that gives us a clear picture of the drug's safety margin. A higher TI means a safer drug. Simple as that. All right, last one for our quick-fire round, a little fill-in-the-blank for you. This term describes the absolute peak performance of a drug, that plateau we saw on the curve no matter how high the dose goes. What is it called? And the answer is efficacy. Excellent work. It's so important not to mix up efficacy with potency. Remember, efficacy is the maximum effect a drug can achieve, while potency is about how much drug you need to get an effect. A very potent drug isn't always the most effective one. If you found this session helpful, please do me a favor. Like this video and share it with your friends and classmates. Keep studying hard, and we will see you in the next one.